Here is a cascode amplifier which is similar to a normal amplifier. This is your driver amplifier M1, which has a all standard value of W by L, Vt, etc., etc. Series to that M1, there is another transistor M2. Please look at it, this is very relevant and good concept to understand. There is another transistor in M2. Please remember, this is common source. M1 is a common source system. Input is at the gate, source is grounded. Whereas M2 actually has a DC potential at the gate. For AC, what is it? Ground. For AC, it is ground. So what kind of this amplifier or circuit will be? Common gate. It's a common gate. We have already done common source, common gate, common drain. So now I say this is a common source amplifier over which we are sitting a common gate amplifier, and it is biased by a constant current source I. Now this is, I told you other day, there are different way of biasing circuits. One is by resistance network, the other of course is by active load like a diode connected loads or a current sources as shown here. They can be also taken from Miller sources, okay, mirrors, not Miller, see mirrors, current mirrors. So it is biased in such a way that both M1 and M2 are in saturation, okay, is that point clear? So the first problem one can see from here, if you have drawn the circuit, rest you do not write, just listen and then think. If M1 and M2 are in series as shown here, in normal case if M2 would have been absent, only M1 would have been there. So how much would have been supply? This is our VDD. Let us say source requires some drop, but the most of the VDS would have come in M1, is that clear? Most of the drop would have come in M1, so VDS would have been guaranteedly larger to make it in saturation. Now I want two transistors M1, M2 also to be in saturation. If they are to be in saturation, this voltage should be sufficient enough that VDS2 plus VDS1 should be such that both makes it in saturation. Is that clear? That means power supply needs to be slightly boosted, because otherwise most of the voltage goes here, then you have nothing left but to make them both them in saturation. So one of the major problem in cascodes are you may require larger power supply voltages, okay. It is not very true what I am making, but roughly larger than the single stage amplifiers. I won't say large or something, because also made in the chips, so it cannot be more than 1.5. Also we can adjust VDS, we can adjust VT, and therefore VGS minus VT still can be smaller than VDS. But irrespective whatever number I choose, I need larger drops for M1, M2 to be saturation. This is one AC problem one you should understand. Now right now assume this current source is ideal and we say its output resistance is infinite, okay, infinite, is that okay? This is a cascode amplifier, is that clear? These sentences are written just for the sake of it, you need not, because I already explained you what I am talking. These are some, okay, basically I am saying this is driver, this is the gate, common gate transistor, this is the essentially current source biased. Now I want to analyze what is the condition, what is the criteria I said last time to make cascode better than cascade. That normally I say FT or unity gain amplifier frequency or the gain bandwidth product as we call GBW, that is constant for a normal common source or any amplifier. So if I increase gain, bandwidth goes down, if I increase bandwidth, gain goes down, is that clear? And the maximum frequency is unity gain frequency, is that correct? You can't go beyond that, because why? Because beyond that gain is minus dBs, means less than 1. So we have to now worry that how can I increase gain without actually losing on the bandwidth or without getting that cutoff point to be any different. If I remain there and still boost the gain, then I achieved something which was not possible in a single stage, okay. That first case gain bandwidth constant or FT is constant is essentially called the figure of merit. You can't go beyond that now. Now I want to say even at that frequency gain is higher. If I do that, then I have achieved something. Is that clear? And this is exactly what Cascode is trying to do. In this circuit, if you see carefully, the gain, there is no additional load resistance I have put here. The load resistance is essentially due to M2 M1, okay. Some combination of this will lead to RO, and this R is also parallel to this R of this source. Is that clear? Why? Because this is ground for AC, so this R is also parallel to RO of this combination, but that we treated as how much? Infinite. So essentially I say this RO equivalent what I am going to see here is the only load resistance I have, and therefore gain is GM times R0, okay, and this R0 we will call RO effective, because without this whatever is RO for this, and with two of them whatever we will call it, say we will call it RO effective. So if I can make GM RO effective larger than GM RO with, and what is the bandwidth frequency, I will just show you, GM by C. So if GM by C is not touched and I increase R0, then I am increasing the gain with not losing bandwidths. Is that clear? So essentially what Cascode is trying to do is to boost output resistance without losing anywhere in GM factors. Is that clear? That is exactly what we are trying, and this is an achievement which is actually not, device is not able to tell us directly. It is, we say device is always cut off, it can't go beyond. Now I am circuit way I am showing you, I can beat the system. Okay, this is the trick in analog, how to beat the system. Some cost will pay somewhere which we are not actually telling, but at that cost I will boost this gain without losing the bandwidth. Is that clear? This is why cascodes are used. Where do you use cascodes? Where you want gain boosting, okay, without losing the bandwidth. Okay, here is that. We wish to find GM effective and R0. I had a tendency to earlier, of course this is my old papers, and this, since I used to use R instead of R0 conductance, GO is nothing but 1 upon RO, okay, GO is nothing but 1 upon RO. So I want to calculate for this cascode stage a GM effective. What is GM effective? If the M2 would not have been there, there would have been only GM1. Is that correct? With M2 present, the effective GM is, we call GM effective, and we derive that. Let GM and GO1 are the transconductance and output conductance of transistor M2, and GM2 and GO2 are similar numbers for M2. Names GM1, 1 is for M1, 2 is for M2. Is that okay? So if I define that GM1 and GO1 and GM2, GO2 are the for transistor M1 and M2, by network theory, the small signal current flowing in this both transistor is I, which is equal to GM effective times V in plus GO effective times V0. This is a simple 2-port network. If you are not done so far in your network course, do it again. Otherwise, it's the easiest way to represent a 2-port outputs. Okay, I is equal to GM effective V in plus GO effective V0. Okay, if you cannot, I will show you how, but otherwise you should be able to write any 2-port network in and out, V in, V out, and you will get these expressions. Okay. Now in this figure, I call this voltage as VO1. This of course I still call it V0. Output of, we are not taking it, but the drain voltage of M1 we defined as output 1, VO1. Is that okay? Definition, nothing great about it. However, if you see carefully, the VO1, which is the drain voltage of M1, is also acting like a source voltage of M2. Is that point clear? VO1 is the drain voltage of M1, but it also source voltage of M2. Okay. Now do you get the point? So VGS is still available. If this is your 0, for example, for AC also 0 minus VO1, which is good enough because then VGS minus VT still will be possible. Is that clear? So this is the trick which I played. I said okay, I put a series there. The drain voltage of this is same as source voltage of this, and therefore I can say my VGS is still plus VO1, and if that is larger than this, it should still conduct. Okay. So this is what I did, I trick on that. For AC signal, that is what I say, VGS2 is 0 minus VO1 is minus VO1. Now from the current equation which I wrote, I is equal to GM effective into Vn plus GO effective times VO. If I make VO 0, do you get the point what I am saying? If I make VO 0, I upon Vn is GM effective. Is that clear? I upon V is GM effective if V0 is 0. Maths. Okay, if V0 is tends to 0, I by Vn is GM effective. So I write GM effective is I by Vn when V0 is 0. By same argument, GO effective is I by V0 when Vn is 0. In equation, do you understand? You make one port output 0, next time you put input port 0, is that correct? And then you get GM effective and GO effective. I by V is both cases is I by Vn is GM effective, I by V0 is GO effective. Is that okay? Assume we apply if now there is a game we are playing. Okay, what I say is this is DC, so not AC. I at this node I apply V fixed DC value at the output where your V0 is. I apply fixed DC value V fixed. So what is the AC value I am applying? 0. So VO is 0. Is that point clear? VO is 0 when I say I applied fixed DC bias, it can't change. dV by di is 0. So we say is V0 there is 0. So we say assume we apply a fixed V fix at the M2 VO terminal, therefore VO is, that is the condition. What is the condition I was asking for GM effective? That I by Vn is GM effective when V0 is 0. So I made that condition true, and then I write VO minus Vs, which is nothing but variation of dVds2, is nothing but 0 minus, please remember this is 0, this is VO1. So how much is change in VO1? AC value 0 minus VO1, which is minus VO1. So VDS is how much? Small VDS, that is AC, is minus VO1. Now look back the two, for the two transistors I write two currents, though I is same in both transistors. Is that clear? I cannot have two in a circuit, there can be only one current, which is I flowing through M2 as well as through M1. So for a transistor 1, I is equal to GM1 Vin, same two port network. So I is equal to, this is what we say intrinsic values, external resistances we will put later if whenever we need in actual circuit. We want to know intrinsically whether we can break that GM, that is gain bandwidth limits, okay, we can now. So I is equal to GM Vin plus GO1 VO1. What is why VO1? VDS of M1. VDS of M1 is VO1, so VO1. For the transistor 2, GM2 minus VO1, because that is the input now, 0 minus VO1, so this is VGS, plus GO2, again VDS is minus VO1. Is that okay? Just substitute values for both transistors M1 and M2 and currents are same. Please take it, in a circuit same current can only flow, okay. So the at the drain of the M2, I am only still looking at this, that is why it is 0 minus VO1 is VO na, for the VDS for this. Is that correct? That is what I put minus VO1. Is that correct? Okay. Okay, if I do this, I can now find out from the equation 3, VO1 3 or 4, I do not know which one. Oh yeah, 3. VO1 is I upon GM2 plus GO2, just simple maths. Okay, VO1 is minus I upon GM2 plus GO2. Please remember, G's are conductances, 1 upon G's are R's. Whenever you wish it, you can convert to back to R's. Okay. Now this VO1 value which I got from equation 3 can be substituted where? In equation 2. In that case, I is equal to GM1 V in. Please remember what was there, minus GO1 VO1. So it is GO1 times I upon GM2 GO2. So if I collect I terms, I is equal to 1 plus GO1 upon GM2 GO2 is equal to GMV in. Under what condition I have derived this? VO is external VO, fixed DC value, therefore AC VO is 0, and under that case I by V in is GM effective. So GM effective is I by V in GM1 upon this quantity. Is that correct? So I have now derived expression for GM effective. Is that, and condition I have made. What was the condition they wanted me to say? That VO is 0. So I have made it VO 0 and I solved the equation and I got my GM effective. Now I want to see all these values which I put. If I do little extensions of this, I can bring this denominator back to numerator. So the GM effectively GM1 into GM2 plus GO2 upon GM2 plus GO1 plus GO2. Just remove that one part and just put the denominator of this. Now typically lambdas of the transistor is how much? Close to 0.001002 or close to 0, equally saying. So R0s are normally infinite, or even if it is higher, mega ohms, tens of mega ohms, okay, or at least a mega ohm. Is that correct? Unless your current is very very high, R0 cannot be reduced to kilo ohms. If it is very high current, then the power will actually take care of your device failures. So you don't worry on that. Okay. So if I say R0 are very large, what does conductance is smaller or larger? Very small. Normally GMs are the order of 10 to milliamps per volt. GMs are typically of the order of milliamps. This GOs are the order of microohms. GOs are the order of microohms. Is that clear? So I say GM2 is much larger than either GO1 or GO2. So I neglect GO1 and GO2 from the denominator. Same way I neglect GO2 from the top. Is that correct? What is the condition I said? Since R0s are very high, GOs are very small compared to transconductances, which is typically 1 order or 3 order higher. Therefore, I neglect GO2, GO1, GO2, equivalently saying it is GM1, GM2 upon GM2, which is equal to how much? GM1. Is that correct? So even by using a Cascode, how much transconductance I obtained? Same as equivalent of the normal single stage amplifier transistor M1. If I had used only M1, I would have got GM1. With 2 in this also I got equivalent of GM. So what is the, if GM1s are equal, you can say GM is GM1 equal to GM2 also if you wish, and still it is valid for it. If the transistor are identical, you can always use. Otherwise, you can always get accurate value. Please remember, this is the net value I have. But in real life, number wise, GM will be very close to, or sorry, GM effective will be very close to GM1. So if you see this expression again, okay, I'll come back first. Let's keep this and we'll use the bandwidth part later. So what value we have calculated? GM effective. What is the next value I must calculate? GO effective. What is the condition in GO effective? I said gain should be 0. So if I say so, I say Vin is 0. That's the condition you wanted, Vin should be 0. Then I say GO effective is I by V 0 when Vin is 0. Is that circuit okay? Input is grounded, that's what you said, Vin is 0, so I grounded it. I use the same equations of current again for this as well as for this. For the second transistor, I is equal to minus GM2 VO1, okay. What is VGS for this? 0 minus VO1. Please remember, VGS is how much? 0 minus VO1. That is this minus VO1 is appearing here. So the first is minus GM2 VO1 plus GO2 times VDS. How much is VDS? VO minus VO1. So GO2 is, okay, I made a mistake. So I rewrote VO is VO2, which is same actually. So VO minus VO1, this is another equation. Now if I write for M1, I had written it for M2, now I write for M1. Current I in this is GM1 times 0, why? Vn is grounded, so GM1 times 0 plus GO1 times VDS, which is VO1, okay. Yes, bias bias is the capital I, उसको सैचुरेट कर रखा है, इनपुट सिग्नल ग्राउंड कर दिया. This is all ma'am small signal, every parameter I am using right now is small signal, okay. So from this equation VO1 is I by GO1, from this equation 5 VO1 is I by GO1, substitute this VO1 in this expression. Is that clear? From 5, since this term goes I by VO1, I by GO1 is VO1, use this VO1 value here and get new equations now. Is that okay? All that I did from the second, fifth equation I calculate VO1 and resubstitute back in equation. Yes. The biasing DC bias is coming from I source and nothing to do with AC signals. Is that clear to you? M1, M2 are biased. I am not saying this is VGS is biasing greater than VT. Small VGS has nothing to do with bias. Is that correct? This is signal. What is input to this signal is for M2 0 minus VO1 is the VGS power. That is the signal it is seeing it. Is that clear? It's a AC signal. Is that clear? M1 AC signal is grounded, but bias is not removed. Bias is coming from I. I have already told you if I is equal to beta times beta by 2 VGS minus VT square. If I keep fixed I am keeping VGS minus VT fixed, which is biasing it for saturation. Is that clear? I repeat, you have not got my issue. Anytime I say I is fixed, please look at it the way I say it now in once for all. Capital I is if the device is in saturation, assuming lambda 0 right now. So if I is fixed, VGS minus VT is fixed. We make I sufficiently such that VGS minus VT is always less than VDS. Choice of I is such that VGS minus VT is smaller than VDS. So when I fixed active load, which is called current source, I am actually biasing the device in saturation. The choice of I is mine. Is that correct? Choice of I is mine, which will fix my bias for any transistor. Is that correct? Same current is passing in M1, same current is passing in M2. So both will be left in saturation. Is that correct? VGS minus VT for both should be smaller than VDS for each transistor. Is that clear? That I am adjusting externally, which is called bias current. Okay. So all that analysis is clear. All that we are talking is AC analysis and not DC analysis. DC we are assuming that I am keeping both of the first slide I showed you. I is so adjusted that M1 M2 remains in saturation. That I externally I did it. Is that correct? I am not saying that if the voltage goes to fixed value it does not pass a current. Who said you VDD minus VX still I can be adjusted. All that I say as if VOAC is made, I am only looking for VOAC. Now your question is, if I make ground itself there, then the whole of I current will actually go to the ground. So I must put some potential there so that current can keep flowing. Is that correct? Otherwise all of current will be grounded. I want AC ground but I don't want DC ground there. Is that correct? And that is why I say put some voltage there such that the whole current does not short circuit out. It will not go through M1 M2 then. Is that clear? That is why that condition was made. Is that clear to you? Why that voltage was put? Otherwise if I physically ground that, then all of I will actually go to the ground. Physical ground. So no M1 M2 will be on. Is that correct? So these conditions have to be made. So assumptions in through all we are saying, whichever way I do, M1 M2 will remain in saturation. This is DC biasing, nothing to do with AC signals. Okay, AC I am calculating. Is that okay? But that is DC. That decides GMs. 2 beta I under root of that decides GMs. So whenever I fix I am fixing GM. Is that clear to you? I am, as far as, please get confused, remove from this, AC signals theory is based on values of DC you fix. Is that correct? That is what we kept saying. RO is equal to 1 upon lambda times I whatever I fix. GM is equal to under root beta times I. So once fix I fix both GM and R0. Yes. But that is a DC current. Yeah, but that is what AC, what is the AC slope at any point is the slope we calculate. What is the theory of small signal we discuss all these ways, that at that point the variation is linear enough that we do not have to say major value changes, DC value does not change. Yeah, it does, IDC plus small IDC will come. But that current is how much? Say it is, I am putting 5 milliamps or 1 milliamp and this is microamps. 1000 times less or even lower. Is that clear? That on any small signal analysis this value is always going to change. You cannot say it's star, but how do I calculate slopes? If anything curve, I take this value and I get a slope here and I say yeah, within this small change I put, yes, two values are actually being changing. There is nothing I can do about it. But this value being what the change here and here is negligible. That is what ACs are all about. Correct. It is always possible. Power supply will adjust to that. Small AC variation will override all the time on DC. Okay, always. That is what we are, and when we want to get output, we remove that DC part by putting a capacitor so that the DC does not go to the output. Is that clear? That is what we have been doing all through so far. Is that okay? Okay. Okay. Sorry, he is right, and I think I must thank him for getting clarifications. Otherwise, I will be doing and at the end everyone will confuse, myself and yourself. Okay. So if I substitute VO1 into I second, third, whatever number of that equation I have, to equation 2, then I rewrite I is GM2I by GO1, GO2 V0, GO2 minus I by G. Is that clear, ma'am? Is that just substitute VO1 in upper equation and you get this equation. I forgot this term, so I rewrote again. So I is equal, collect I terms on the left, the other terms is GO2 V0. So sum of this is 1 plus GO2 plus GO1 plus GM2 by GO1 is into I is GO2 V0, and then what is the definition of GO effective? I said I by V0 when Vin is These equations were derived based on V in is 0. So GA effective is I by V0, which is GO2 upon 1 upon GO2 by GO1 plus GM2 by GO1. Again if I linearize it, GO1, so I get GO1 GO2 upon GO1 plus GO2 plus GM2, okay. Then if you wish I can write RO effective is GO1 plus GO2 plus GM2 upon GO1 GO2, or can be written as 1 upon GO2 upon GO1 plus GM2 upon GO1 GO2. Is that okay? What did I get? I get RO effective. Is that correct? I got RO. GO effective is 1 upon RO effective. So I just got RO effective, which is 1 upon GO2. What is 1 upon GO2? RO2. 1 upon GO1 is RO1. Now if I do this, you can see from here RO effective is RO1 plus RO2. This 1 upon GO1 I made it RO1 into GM2 by GO2, or GM2 RO2 also you can write, okay. But what is GM2 by GO2 or GM2 RO2? Gain of M2, gain of M2, AV2. So I write RO effective is RO1 plus RO2 AVT times RO1. Is that correct? If AV is large enough, how do I make AV large? By increasing the W by L of those transistors or by increasing the currents, okay. If I increase sufficiently AV, which I can, then RO effective is how much? 1 plus AV times RO1 plus RO2, and if the gain is say 50 or 100, how much is RO effective? 100 times RO1. If I do not put M1, M2, how much would have been output resistance? RO1. If I put M2, how much I got? Gain times RO2 I got. Is that correct? Plus RO, of course this plus term is there, but this is much higher. So what I have boosted? The output resistance got boosted gain times in this cascode. Then we say AV effective is GM effective by GO effective or RO effective essentially. So I get GM1 into RO2 plus 1 plus AV1. If I expand this well, please note down this. AV effective is GM effective upon GO effective is minus GM1, RO, this I put here, RO2 plus 1 plus AV2 RO1. Then I say this can be written as GM1 RO1 is AV1, this is RO2. Assuming GM1 is equal to GM2, everything is same, then AV effective will be equal to AV square. If GMs are equal, that is sizes are equal, same current is flowing, GMs will be equal, so AV effective will be equal to AV1 square. So what did I boost? Gain. Is that clear? Gain I boosted how much? Square, AV square. I could have boosted my gain of any amplifier. Let us say I have two such amplifiers, A1 and A2. Then what would have been, if this is my V in, this would have been also output of this, VO1 would have become input for this, and next gain times it would have come like this, okay. And if they are equal, I still could have got the net gain is A square. This is called cascade. Output of first is given to the input of next stage. So gain boosting is not very difficult. I could have put two in series like this, cascade them, and I got the boost of the gains, okay. So what did I achieve out of that? That is what the cascode is different. What is that we achieved? Please remember, gain boosting is not the only thing we achieved. What did we held constant in that? GM. We even with cascode we maintain same GM. GM1 is GM effective, okay. Because of that thing, one can see the gain bandwidth product is GM effective by Cin, GM by Cin, because GM is same, GM1 is same, is that correct? So since if all GMs are equal, one can say gain of a cascode is gain single stage square, but the bandwidth remains same. Is this would have been possible in cascade? No, because full system would have gain bandwidth constant. So if I increase gain, what could I have lost in that? The bandwidth. So cascade stages actually improves gain but lose on. Okay, so this have you got the point advantage of cascode over cascade? That the cascade amplifiers boost gains at the cost of bandwidths. Cascodes boost the gain without losing the bandwidths. Is that? But what is the penalty I am paying out of all of it? I may require larger power supply voltages. Is that correct? At the cost of VDD, I have achieved this. Is that clear? So is that point clear? So what is the advantage of cascode word? Cascode is a very interesting device that it allows you to boost output resistance without changing the transconductance, okay, and that's something which no one else can achieve. This is normally not done so much in discrete amplifiers. This is always done in integrated circuits because that's much easier to adjust that GM1, GM2, identical ROs, everything is possible on single chip. Two different devices if you take on a breadboard, they will never be identical. Try any number of times. Take 1,000 of such devices, measure IVs and CVs of them, nothing will be equal. Okay. So, in a discrete, such experiments are very difficult to prove sometimes. But in case of ICs, since the areas are very small, everything is almost identical. Therefore, integrated circuit use almost all such tricks, more so in analog ICs or mixed signal ICs. Since future is only on ICs, not on discrete. So why do we do discretes? Because discretes tell you which is the way you should go for ICs. Okay, unless you know discretes, you can't do IC. Today I showed you same methods can be extended for IC designs. Is that clear? Okay, so next chapter for our course is very important. Frequency response of amplifiers. Now our assumption so far that there is a frequency of signal which device does not bother and it amplifies output at the same frequency. Please take my word, what I am saying is, let's take an amplifier and I have an input signal at 20 kilohertz, okay, and a gain of say 100. So I know 1 millivolt of 20 kilohertz will become 100 millivolts at 20 kilohertz at the output. Let us say I change that 20 kilohertz to 50 kilohertz. I still believe that it may still come so many millivolts at 50 kilohertz. If I increase to megahertz, then I am not very sure whether the same 100 gain will remain for the amplifier even at 1 megahertz or above, okay. Which means the gain is also not only a function of V0 or V normal magnitude wise, but also is a function of frequency. So I must, for an amplifier, what is the condition I must have? I must know the region of frequency band as we call, say F1 to F2, in which gain is constant, so that I know any frequency in this range will get amplified normally. But beyond that the gain may not be same, or before that F1 also may not be what you want. Is that clear? This is what we want to know. This is essentially called the bandwidth or midband frequencies of an amplifier. I want to know where is the midband. What is midband? Where the gain remains constant. So first thing, to know this, I must now first do a mathematics to some extent and see how do I evaluate the frequency response of any system. Okay, amplifier is a system which has some input, some output. Any system has input and an output. Why I am saying this generalized? Because this theory which we are talking has nothing to do with electrical networks, it can be applied to any energy, mechanical or any kind, okay. This is what control system is all about, is that correct? We are only looking electrical signals, but this is true for any other signals as well, okay. So let us start with our electrical, for example. I hope that in your maths course, if not so far, must have done Laplace transforms. If you have not done it, do it. So we do j omega is what we call S, which is called S domain analysis, and if you have a system which is shown here, any typical system which can be electrical in our case, then it has Vn which is a function of frequency, that means frequency can, S is j omega, so omega changes, Vn changes. Please remember, anything which is written is only right now imaginary quantity, but there will be also real quantity, S is equal to sigma plus j omega, is that clear? There will be a real quantity plus imaginary quantity. Right now I am assuming everything is imaginary, okay. But in future, in real life we will use that real quantities also. There will be some output, and please remember there can be many possibilities, V voltage input, voltage output, voltage input, current output, current input, current output, current input, voltage output. 4 possible outputs for 4 possible inputs. This is called ratio of output to input function is called transfer function. Ratio of output to input is called transfer function. So how many kinds of transfer function in normal this system could be? 4 kinds. Voltage by voltage will be voltage gains, voltage in and current out is transconductance gains, current is input and output is current, current gains, current is input and output is trans resistance gains, is that correct? So 4 possible gains can be possible, and there can be 4 therefore different. We are right now using voltage transfer function. Why? Because in most cases amplifiers we are using are voltage amplifiers, but later we will see it can be also any one of them as well. A typical transfer function of a network shown here is Hs, or which is H omega is V0s upon V in S, and can be written as arbitrarily in this form. K is constant, independent of frequency. In numerator you have a series of terms which is S minus Z1 into S minus Z2 into S minus Zm divided by S minus P1 into S minus P2 into dash 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 S minus Pn. This Z is called zero of the function, Z's are called zeros of the function, and P's are called poles of the function, is that correct? This is nothing to do with network per se, as I repeat this is true for any transfer functions, okay. Why are we looking into this? Because let us say, okay, maybe there is another slide here or just from here, if S is equal to P1, how much is Hs? If S is equal to P1, how much is Hs? Infinite, Hs goes to infinite. If S is equal to Z1 or Z2 or Z3, how much is Hs? 0. So pole is essentially saying the transfer function value goes to infinite, and 0 means it goes, transfer function value goes to 0. This is magnitude wise what we are trying to say, is that clear? So poles and zeros are those values of frequencies at which the transfer function may become 0 or may become or tend to infinite, is that clear? That is exactly what mathematically we are saying. How does it circuit wise we see is very important for us, because there is where we are worried about, okay. Is that general idea of transfer function clear? Any, and please remember for there in our system we may use either of the 4 in actual amplifiers. I may use a current amplifier, then what is the output will be I0 and input will be In. So there will be AI, AV, RI, R and G both possible in this case, is that clear? So we only right now look for voltage transfer function, but do not worry, it is true for all kinds of transfer functions. Here is a simple circuit, okay. there is the input V in AC, there is a series source, series RS, of course, since there is no MOS transistor, RS is the source resistance. There is a capacitance of C which has an impedance of 1 upon Cs, and there is a load which is RL, and let us say by Kirchhoff law, if the mesh current is IS times RL is V0, is a function of S. Is that correct? V0, IS is the current in this mesh or loop, so I times RL is V0. Okay. But how much is IS? There is only one voltage source, V in divided by the net impedance, this plus this plus this, RS plus 1 upon CS plus RL is the net impedance in the loop, series impedance. So V in upon this is IS, rewrite in V in into CS upon RS plus RL CS plus 1. Maths, nothing great, just take CS like this and bring CS above. Okay. Please remember, this is not C's of S, S of means C is small s, this S is the Laplace transform S, j omega term. Okay. You can write j omega C as well if you wish. Okay. So V0 S upon V in S is RL CS upon RL plus RS times CS plus 1. This is the transfer function of this. Simple. What is, where is the capacitor in this circuit? It is in series to the source and the output. Where could have been otherwise? Across RL also I could have a capacitance, it will be called parallel capacitance. This is called series capacitance for namesake. Okay. Okay. Is that okay? Obviously, if the frequency is 0, S is 0, you can see what is the transfer function, RCS is the numerator. If S is 0, HS is 0. So there is a 0 at frequency 0. Okay. So a 0 exists at omega equal to 0 or F equal to 0. Okay. However, if you look at the transfer function again, okay, this to become 0, RL plus RSCS plus 1, then we can say RL plus RSCS equal to minus 1. At that time HS will become infinite, and this minus sign is avoided in CAD because it is always on left half plane, but just for the sake of it is 1 upon RL plus RS times C, and this is its called is the pole for this transfer function. Please take it. What is RC called? R into C? Time constant. Is that correct? So I define RL plus RS times C as the time constant tau s, okay, as the time constant this. Okay. Then, is that okay? 0 exists at 0 and pole exists at 1 upon RC of this value or 1 upon tau s. Okay. However, we can rewrite the transfer function again. H is V0, please look at your function V0S upon V in S. I use that RL plus RS, I bring it outside. Okay. So I get RL upon RL plus RS and I multiply it by RL plus RS. These are same terms. Okay. I just multiply and divide. So I get RL upon RL plus RS is RL plus RSCS upon 1 plus, and use RL plus RSC as tau, and this RL upon RL plus RS as K, then HS is K times tau s S plus 1 plus tau s. Is that correct? All that I did, because on the numerator I don't have tau getting, so I multiplied RL plus RS and divide RL by RS, RL plus RS. So this also become tau s. This is a constant. Why it is called constant? It is independent of frequency. So it is called K, tau s s upon 1 plus tau s s. So we now say if it is a voltage gain, transfer function is voltage gain, then AVS is RL upon RL plus RS. If I write j omega tau s upon 1 plus j omega tau s. Is that correct? Now one can see now you have 3 terms here. What are the 3 terms you see? One is this term, the second is this term, and third is 3 terms. Are you sure? You have 3 terms, independently can be seen, 1, 2 and 3. What I am going to do, I will actually see response of each function with frequency initially, and then what I say, if they are all together, that is this one, how will they look? Is that correct? I want to find variation of gain with frequency, that is my aim. Frequency response, you said, no, I want frequency response. So I want AV as a function of omega, I want to find. So I made a trick to understand. In future I may not do it, but initially I say, okay, I see now 3 functions, one of this, the other is this is in numerator, this is in denominator. So I use my tricks and I say, okay, first I get the magnitude. I want how many quantities I should really find for any complex function? Magnitude and phase. So first derive the phase. I want to know the magnitude of the gain as a function of frequency. It is RL upon RL plus RS omega tau s upon 1 plus omega square tau. This is just A plus JB is and magnitude is under root A square plus B square. Is that clear? So I just substituted the magnitude values, where omega of course is 2 pi f. Okay. So if I take AVF, I can write RL upon RL plus RS 2 pi f tau s 1 plus 4 pi square f square tau s square to the power half, same function rewritten in the form of frequency. Is that clear? The function which I wrote here is same as this, only thing now written in 2 pi f forms. Okay, omega is 2 pi f. Now I start taking, this is gain, and gain can be expressed in some numbers which is called decibels. Okay, why we use decibel as a word? Because essentially the decibel was found for measurement of noise or measurement of audio signals initially, but they defined 20 log P2 by P1, or rather if I put 1 meter is called dBm, is some function power in dB. But since in our case power can be IV and I being same, we can write 10, I am very sorry, this will be V square by R, this will be V square by R. So if I say gain voltage kind of this is 10, square means 20 d log V2 by V1. So AV in dB is 20 log V2 by V1, which is gain. Okay, is that correct? So if I want to find any dB values, all that I do is 20 log 10 of magnitude of this value, which is AVJ omega. Is that clear? 20 log V2 by V1 is the voltage gain in dBs. Okay, so but V2 by V1 is the gain actually what we have found. So I actually write this function and start, in log, what is the log A into B by C will be log A plus log B minus log C. ये log इसलिए किया था. Okay, ये 3 terms को अलग अलग कर दें. So the first term is 20 log RL upon RL plus RF. The second term will be 20 log 2 pi tau s, and the third term is minus 20 log 1 plus 2 pi f tau s square, or 4 pi square f square tau s square. Okay. So let's start plotting individual terms. Please remember, if I want this total, what is the theory I am applying when I say like this? What is the theorem called? This plus this with a minus sign. What is it called? Superpositions. So I actually do individuals and then superimpose them to get the net AVF in dBs. So the first term, which is 20 log RL by RS, I plot as a variation of frequency. Okay. Whether it will be less than 1 or more than 1, because this is RL and the denominator is RL plus RS, so it will be less than 1, therefore minus. Okay. So I say from 0 dB, it will be some minus value, which is 20 log RL plus RS, some value, okay, depending on the ratio of RL and RL plus RS. Okay. Please remember why minus, because denominator is higher than the numerator. Okay. But this is always constant, because there is no term in this which is frequency dependent. So this remains constant. Is that correct? Why I do all these simple things first? Because I want to make it very clear that things are trivial in real life. Okay, unnecessarily don't get excess. Or analog course बहुत भारी है. What is the value? I repeat, 20 log RL upon RL plus RS has a fixed value throughout any frequency. It remains constant. Is that okay? Is that okay? Now use the second term. The second term is 20 log 2 pi tau s. Okay, 20 log 2 pi tau s. So I say at f is equal to 1 upon 2 pi tau s. Please take a frequency. F is equal to 2 pi tau s. What is the value of bracketed term? 2 pi f tau s is how much? 1. How much is value of log 1? 0. Log 1 is 0. So it's a 0 dB. Is that clear? F is equal to 1 upon 2 pi tau s, if that is equal to 1. So at f is equal to this frequency, the gain is 0 dB. This second term only I am saying, not the net one, only second term. If I multiply it by 10 frequency, okay, that is, if this becomes 10 upon 2 pi tau s, okay, then what will be the value? 2 pi tau s is 10. How much is log 10? Log 10 is 1. So how many dBs? 20 dBs. So at 10 upon 2 pi tau s, how much is the value of gain, this function? 20 dB. Is it okay? 20 log 10 is 20 dB. But I take another other side values. 0.1 upon 2 pi tau s, that is 1/10 of that value. So what is the, again 1/10 means how much? Minus log 10 means how many dBs? Minus 20 dBs. Is that ma'am clear? If 0.1 means 1 by 10, 1 by 10 means log में minus log 10. So log 10 is 1, so minus 20 dB will occur at 1/10 of this frequency, and plus 20 dB will occur when it is plus 10 times the frequency. 10 times this frequency you are 20 dB, 10 times less is minus 20 dB. So if you go from 1/10 to 10, how much gain dBs we have increased? 40 dB. In how many orders of frequency? How many orders? 2 orders, 10 and 10. Okay. So per 10, which is called decade, how much dB we are increasing? 20 dB. So the slope of this transfer function gain for the second term is 20 dB per decade. Slopes are called 20 dB per decade. Is that correct? Why decade? Because every 10 times this 20 dB will come into picture. Okay. 100 if you do it, how much? It will be 40 dB. If it is 1000, it will be 60 dB. Is that clear? So every times you increase 10 times, another 20 dB will appear. Is that correct? So 20 dB per decade is the slope for this. Is that correct? By same logic, if I do the third function, which is 20 minus 20 log under root of 1 plus 25 tau s square, up to when the f is equal to 2 pi tau s is equal to 1, how much is the value of that value should be at this frequency? Minus 20 log of, no not 2, root 2, 1 plus 1 under root, is that correct? So under root 2, which in numbers it is 3 dB, minus 3 dB, is that correct? This is minus 3 dB. So what is it showing? That at f is equal to 1 upon 2 pi tau s, the gain has fallen from 0 to 3 dB down. At this frequency, please remember initially how much is the gain when f is smaller than 1? What is this part I am showing you? When f upon 1 upon 2 pi से बहुत छोटा है, so 1 plus 0 as if हो रहा है, so I am getting a 0 dB gain. As I start increasing the frequency, that 1 upon 2 pi term coming into picture, and then we may start saying the gain will start reducing. At that frequency the gain would have fallen by 3 dB, minus 3 dB, essentially 0 to minus 3 dB. Now this further down, if you say what will happen, 1 may be negligible or this, and again 20 log decade it will start, if you increase f 10 times, again it will come the same way, 20 dB per day. So now you can say 3 functions I have plotted. Which ones? First one is this, second this one is this, and this one is this. So I have 3 functions which I created, and I now plotted 3 different frequency response term for 3 terms. Okay. But what is important for us? I want addition for this. Okay. So if I add all of them together, okay, and this value is 0 dB. Please take it. थोड़ा सा एक बार फिर से वो फंक्शन देखते रहें तो अच्छा है. Please remember this is less than 0, some value. Okay. From this frequency onward, the gain is going towards, this is 0. Please remember, if I am adding now all 3 of them, this plus this, and this is 0. Okay. So if I add all 3 there, then what do I get? Initially, of course this may be RL upon minus 20 this, and it starts rising up to what value it was rising towards 0 dB? 1 by 2 pi tau s. But actually that value is not, this is 0, but this value from the third one is how much? 3 dB down. At this point it is not 0 plus minus 3 dB. So it is somewhere minus 3 dB. Is that point clear? Up to this frequency, at this frequency how much is actual gain? Minus 3 dB. One is 0, the other is minus 3 dB. So this is minus 3 dB. Okay. Then if you see further, the gain starts falling and the other one is gain starts. Please remember, this is 20 dB per decade, this is 20 dB per decade down. So what is the sum total of these 2? This is 20 dB, this is plus, this is minus. How much is? Constant, 0. So afterwards the function becomes constant. Plus 20, you can see geometry wise, plus 20 minus 20 is equal 0 0. Okay, per decade 20 dB it will rise, 20 dB it will decrease. So essentially no. Oh yeah, it's offset. Yeah, you are right. I should have put instead of 0, but assuming that term is 0 small, and okay, you are right. What he is saying is correct. I should not, this term is not 0. What he is saying is this term is not 0. Right now I neglected that term. Okay, you are right. I fully appreciate. So what is it trying to show you? This means, please remember, this is the crux of it. Now this is the name which I am now going to give you. This is the frequency response of the transfer function I have used. This is the 3 dB point, and what is this point is occurring at where? F is equal to 1 upon 2 pi tau s. Beyond this frequency gain is becoming constant, gain is becoming constant. If I draw two such lines, one line straight way and the other from this 3 dB point straight way like this point essentially represent 1 upon 2 pi tau s, this point, okay. This is called corner frequency, this is called corner frequency, and actual curve is asymptotically following these two curves, is that correct? Asymptotically, this is your real curve, this is the curve which I am now modeling to, is that clear? This is the real value, is that correct? This is what I am now saying equivalently, two lines like this, here it may be. So this frequency is also called 3 dB frequency or minus 3 dB frequency, but this is called corner frequency. This thinking that such 3 dB points can be put sharply like this was first suggested in 1940 by the famous mathematician, or rather control system man. All control systems are maths people, okay, or vice versa, all maths people can do controls, okay. What is the name of that person? Bode, okay. Bode or Bode, some people say, I don't know, I call it Bode and here, so I will call Bode. Mr. Bode first time suggested that to look at the response, I must know the corner frequency, because I am interested in below which frequency gain is higher or lower or above which. Actual value I may calculate by actual function, okay, 3 dB down, but I am not interested in the value of that, I am interested which is that frequency, which is called the corner frequency. Therefore that asymptotically substituting that essentially was first suggested by Bode, and therefore all frequency response plots were called Bode plots. Of course this is only amplitude, but we will also see next time frequency phase part of the frequency, okay. Is that clear to you? Is that clear? So why it was called Bode? This first part is not Bode's. People even now call this Bode's. Actually no, Bode only suggested they should have a corner frequency concept, which was first time suggested by him. Because in real life I want to know what is the frequency up to which gain I should not use or beyond which I should use, or vice versa. I only want that value. The actual magnitude may be 3 dB now, who cares? I want that frequency, is that correct? And I will be always away from those corner frequencies, okay, to be guaranteedly on this side or on this side, is that clear? That is why these plots were called Bode plots. So in future we may not draw the actual curves, we may draw always Bode plots, okay. But when you ask to do real, you must do asymptotes on that both sides. For example, something like this occurs, so you know it will be something like this, is that clear? It will be asymptotic here and same way here, okay, that is actual values, but we will only draw like this, is that correct? This is how Bode thought, and that is what the Bode's diagrams are all about. See you next time.